approximation to roots. So no, it's finding those x-intercepts. Sometimes they're easy to find, but sometimes they're hard. Sometimes we can't solve the equation. So we need a way to approximate. And we're going to look at two methods. The first one's a really simple idea. It's just simply halving the interval. Okay? And it works really good if the curve's continuous. So if the curve is continuous from A to B, there's some random function. And I know that the solution exists somewhere between A and B. And I know that because when I sub in A, I get a positive value. And when I sub in B, I get a negative value. So somewhere in between, it must be 0. Halving the interval, we basically find the average of A and B. Find what the halfway mark is. So all right, let's have a look at this one. X to the power of 4. I mean, it's a hard equation to solve. It's not easy to find the solutions. But I know there's a solution in between 1 and 3. I know that because function 1 is negative and function 3 is positive. And we're talking about a polynomial, so we know it's continuous, somewhere in between. So if I average that out, I get 2. Okay, all right, well, maybe the solution is 2. Substitute it in, it's not. No, it's 1. But now I know that, hang on, that gave me a positive answer. So if I imagine my number line there, 1, 2, and 3. 1 gave me a negative answer, 2 gives me a positive answer, 3 gives me a positive answer. I can now trap it in a smaller interval. I now know the solution must be somewhere between 1 and 2. Okay, well, I'll average them out. 1.5, let's see what happens there. Sub it in, I get a negative number. All right, it's not the answer, but now I know that that solution must be between 1.5 and 2, because 1.5 is negative, 2 is positive. I can trap it again. So I'll do it again. 1.75. Oh, that's negative. Try again. And, all right, 1.88. Now, how many decimal places do we want the accuracy on this? Did we say? Okay, so basically I want to keep doing this until I get the same answer to 2 decimal places. So 1.88, no. All right, that's negative 2.75. But now I know it's in between 1.88 and 2. So 1.94. Notice I only bothered doing it to 2 decimal places there. So 1.94, no. Sub it in, and I know we're in between 1.94 and 2. Let's try again. 1.97. Ooh, look at that, 0.001. Don't let the answer fool you. Yes, that is 0 to 2 decimal places, but that does not mean it's the right answer. Right? Because the graph might do something really weird. I mean, it might be really close and then shoot up or something like that. So it's not the answer we want to 2 decimal places, it's what we're subbing in we want correct to 2 decimal places. Okay, we're in between 1.97 and 1.94. Okay, the average of that is 1.96. Try that, minus 0.3. Okay, we're getting closer now, because now that I'm in between 1.96 and 1.97, to 2 decimal places, I've got the answer. It's either going to be 1.96 or 1.97. So the question is it closer to 1.96 or 1.97? And that's where I now need to go to 1 more decimal place. So I can see which side of 1.96, well, in the middle would be 5. Which side of 1.965 am I? So let's have a look. Sub in 1.965, I get a negative number. So actually, 1.97 was the correct answer. So had I made that mistake back then, I would have actually got the right answer. But that's just a coincidence. So all right, I now know that I'm closer to 1.97. So to 2 decimal places, there is our solution. So depending on how good, I guess, our first interval is, how long it's going to take us to keep trapping it and trapping it. And then a test. They're not going to ask you to just keep going. They'll probably say, oh, just use 1 application to get a better estimate or something like that. That's what they tend to do, unless we're feeling mean. Newton, here he is again. Oh, Newton, where would we be without him? Newton's method of approximation is quite clever. What it does, similar idea, okay, but it's really key that the first approximation we make is good. Because what Newton's approximation does, here's our random curve. If I pick a good first approximation, I want to find this solution here. And let's say I'm estimating it at x naught. Now x naught's not the solution, but what our formula will do is it finds where the tangent then cuts the x-axis. So depending on how steep the curve is, I might get there really quick. Or if it's shallow, it might take a while. So basically the formula will find where that tangent cuts the x-axis and we'll say, okay, that's going to be my next approximation. Now, obviously, if my first approximation is a stationary point, I'm going to have a problem. Because that tangent's horizontal and it will never cut the x-axis. So Newton's method will just fail altogether. Okay, so that's why the first one needs to be a good approximation. If I was over on the wrong side of a turning point or something like that, it would direct me to a different solution, not the one I'm looking for. So if you got an idea of what the graph looks like, that can help us pick a good first solution. So the slope of the tangent, I could work it out. Don't worry, we don't have to do this each time. This is just showing us how Newton's method is created. So basically, we're going to find the equation of this line and then find its x-intercept. So the slope of that tangent turns out to be there. So there's our derivative. We're saying the derivative is equal to that slope. Point slope formula, rearranging it, and we eventually get, there's the formula. So it actually is a rearrangement of the point slope formula, and we put it in. So our next approximation, we get our first approximation, and from it we subtract this fraction, where we put the function value over the derivative. Now, the common mistake is to get that the wrong way around, but the way to remember it is, if f dash x is 0, it's going to fail, because that's the slope of the tangent. Right? So you can't have 0 on the bottom of the fraction, we can't have, that's why the derivative has to go on the bottom. And then you would just keep going till you get your desired result. All right, let's do the same question. We need to pick a good first approximation. So what shall we pick? And don't say 1.97. Okay, remember we have no idea. But we do know there's an answer between 1 and 3. What would you think a logical choice would be? Okay, so my first one is going to be 1.5. It's logical. All right. So we need the function, we need the derivative. And remember, the equation you're solving, you always make equal 0. Equal 0. In this case, it was anyway. So function 1.5 is negative 10.9375. There's our derivative. Sub it in. Oh, 2.21. All right. Let's do it again. There's function 2.21. There's the derivative. Sub it in. I get 2. Maybe I should have started with 2. Function 2. Derivative. That's why I didn't start with 2. Because I knew it would get me to the answer straight away, and I didn't want to do that. I wanted to do it a couple of times. So 1.97. Mind you, remember, we don't know that's the answer yet. So sub it in again. Oh, 1.97. So obviously I'm going to keep getting 1.97. So that must be my approximation. So if I want to do something like this, well, let's find the square root of 23. All I need to do is create an equation that would come up with the answer, the square root of 23. And then I can come up with an approximation for the square root of 23. And I guess the most logical equation to pick would be x squared minus 23 equals 0. Remember, you've got to make the equation equal 0. So if that's the equation, my derivative is 2x. A good first approximation, square root of 23. Well, I know the square root of 25 is 5. 5 is probably a good place to start. What I did, it's another way of doing it, is actually creating a formula to sub into. And I guess this is useful if you use a spreadsheet or something like that, because then you can write a formula for the cell and just let the computer do all the work. x equals 5. When I sub that in, I get 5 squared plus 23, which is 4.8. Sub it in again. 4.7958333333, and so on. So it's got it pretty quick there to 2 decimal places, 4.8. That would be the square root of 23. If you don't believe me, get your calculator. Just to finish off with some other possible problems you can have with Newton's method, of course. You can get into an oscillation, which will just enter you in an infinite loop if you do something like this. So here's my random graph. I want to find that particular root. If I take my first approximation there, oh, there's x2. Okay, x2, draw in the tangent. Oh, it's x1. And you'll now just end up in an endless loop because x1 will create x2, x2 will create x1, and so it's obviously we need to adjust slightly or fix it, but we just happen to pick one that landed in that oscillation. Again, as I was saying, if I go the wrong side of the stationary point, I will get to a root, but I'll converge to the wrong one, not the one I'm looking for. So something like this. If I wanted to find that root, and I picked my point over there, oh, it's going to start finding the other solution over there. So, you know, that's a couple of problems you could have. Okay, just a couple of questions to have.